Okay, today I want to at least come close to finishing what we have to say about plastic deformation. And put your thing in. My little connector here fell out. Well, I guess I just have to punch from the screen here. In the stable plastic deformation, well, there are two stages to plastic deformation. If we tool a tensile specimen, above the yield strength, we begin to get permanent deformation. Initially, that deformation is stable, and if we're talking about a tensile bar, it will stretch while preserving its shape. Eventually, we get to the ultimate tensile strength, and what happens there is that the plastic deformation goes unstable. We concentrate the deformation in a neck here at the center of the specimen, and the material then necks down until it finally fails. The thing that is accomplishing plastic deformation in the case that we care about, in the most common case, is the motion of dislocations. Within the material, you see these dark lines, which are dislocations. As the material is deformed, these are electron transparent pillars deformed in an electron microscope up at INSEM at LBL. And as the material deforms, you see these dislocations move. You also see them multiply. I'll show you a movie or two in just a minute. Recall, again, we talked about this last time, the plastic deformation changes shape at essentially constant volume. So it's a shear process. Any stress state we have in the material, we can break it down into the sum of a hydrostatic stress, hydrostatic deformation, and a shape change. The hydrostatic deformation changes the volume without changing the shape. The shear changes the shape without changing the volume. And this shear is plastic deformation. We accomplish shear, we can accomplish shear by moving dislocations, such as the edge dislocation we've seen here. As the dislocation moves, we expand the area over which the crystal has been slipped, and that causes a change in shape, or shear of the crystal. In the more general case, dislocations are neither simple edge or screw, as we discussed earlier, but are curved. The general case would be a dislocation loop, such as shown here. The deformation of the material would be accomplished by expanding that dislocation loop. If we put a shear stress towel on the plane, oriented so as to slip the top of this crystal over the bottom, the force on the dislocation has the magnitude tau b, where tau is the component of the shear stress in the direction of the Burgers vector b. The Burgers vector b is the slip vector, and that has the same value at every point in the interior of that plane. That force acts perpendicular to the dislocation line, and what it's trying to do is to expand this dislocation loop. Because if you move that dislocation line normal to itself, you change the area that has been slipped. If you change the area that has been slipped, the shear stress that is trying to accomplish that slip does work. And that's how you can realize that the force on that dislocation is tau b is perpendicular to the dislocation line, trying to move the dislocation perpendicular to itself, so as to accomplish slip in the direction that the shear stress is trying to make it happen. The subtlety in plastic deformation is that we're concerned about plastic deformation, about the yielding of a material. We test that ordinarily in a tensile test, take a bar, pull it in tension. The actual mechanism by which the material deforms plastically is in fact not driven by the stress that we impose, which is a tensile stress, but rather by shear stresses, and in particular shear stresses that move dislocations in planes that are angled with respect to the axis of the bar. To understand that, if we have a shear stress, P over A, if we have a tensile stress, P over A, along the axis of the bar, and if we consider the force in any plane angled to the axis of the bar, then there will be a shear component of that force. And as we described last time, that shear component is equal to the tensile stress sigma, cosine theta, cosine phi, where theta is the angle between the normal to the plane we care about and the axis of the bar, and phi is the angle between the force, the shear force in that plane, and the tensile axis. This quantity, cosine theta, cosine phi, has a maximum value of 1/2 when both theta and phi are 45 degrees. So the optimal situation is when we are trying to move a dislocation in a plane whose normal is angled 45 degrees to the axis of tension, and we have a shear force in that plane. That will give us the maximum value of the shear stress for a given value of the tensile stress. Now, a dislocation moves. The motion of a dislocation requires the local configuration of atoms. So it takes a force to make it move. It takes a shear force to make it move. And the force that makes it move is called tau c, the critical resolve shear stress. And that is a material property. More specifically, it is a material property for a dislocation of a given type on a given plane. Here, for example, this is an edge dislocation in a simple cubic crystal operating on a 100 plane. And in order for it to move, I have to put a critical shear stress on that plane, which is sufficient to cause these bonds to break and reestablish themselves. If I do that, the dislocation moves. That's the critical resolve shear stress. The yield stress that we actually measure in a tensile test is the tensile stress that we put on, such that the shear stress becomes greater than or equal to the critical resolve shear stress on the most favorable plane. When that happens, we can get deformation, and dislocations can move, and plastic deformation can happen. Well, if the dislocations are actually moving on planes that are angled to the axis of our bar, how come the bar gets longer? Well, it gets longer for this reason. If we have slip on an angled plane as shown here, if our tensile stress sigma gets big enough that we drive slip on a plane that's angled to the tensile axis, then we're going to get this kind of sliding, and the bar as a consequence will get a little longer. What actually happens when we deform a single crystal in tension is that we get slip on sets of planes, usually cross to one another, so we get kind of X-like patterns on the surface, and the bar as a consequence gets longer by slip by the mechanism that you've shown right here. I have a movie showing that. I think it's the next one. Yeah. Let's see if I can get this movie to operate. This is copper. Oops. Now the question is, how do I make this movie happen? Is that working? Yeah, there you go. This is copper, deformed in tension in a transmission electron microscope. There's your stress strain curve. Here's the deformation. Now, can you see that? The deformation happens you can see the lines here. In fact, I'll play the movie again if I can, and you'll see slip happening in this region on planes that are roughly 45 degrees to the tensile axis. These are the active slip planes in copper, and they cause the elongation to happen via the slip mechanism that I just showed you. Let's see if I can make this happen again. There we go. Focus on this region up here. You see that? See the slip happening? See it happening? Sliding, and there's your plastic deformation. A second example, which is maybe a little better because you can actually see the dislocations. This is a single crystal titanium, again, a very tiny sample, so that you can actually see what's happening in transmission electron microscopy, done up at the National Center for Electron Microscopy at LBL again. All right, see the dislocations moving? They're moving and multiplying in that region right there. But back here for something. Did you see dislocation flipping along that 45-degree line? It happens so fast that you can't really, you can sort of see it flash by in the picture. The dislocations go along that 45-degree slip line and leave this deformation, which causes the sample to get longer. And that's basically what's happening in plastic deformation, of course, on a much broader scale. If we turn to a polycrystal, as we discussed last time, if you load up a polycrystal, the yield strength of the polycrystal is going to correspond. Imagine it's completely relaxed. These grains are under no stress at all, which, as I said last time, is an unusual situation. Usually, if you make a polycrystalline material, just because of the way you made it, there are residual stresses in the material. And those stresses some of them will act to favor plastic deformation, lower the yield strength. Some will oppose plastic deformation, raise the yield strength. But if we imagine this to be completely relaxed for the sake of argument, we load it up in tension, then what's going to happen is we're going to begin to get deformation as soon as the resolved shear stress from that tension exceeds the critical resolved shear stress on the most favorably oriented grain in the entire material. When that happens, we're going to get some dislocation glide, we're going to get some slip, and that grain's going to deform. Well, that grain begins to deform, but the grains around it haven't deformed yet. If I take one grain and change its shape and it's still attached to the grains around it, I'm going to put stresses into those grains. So the fact that this grain deforms stresses the grains around it and promotes their deformation. So what actually happens when you deform a polycrystal is you pull on it. Within the polycrystal, you get little islands, little regions of deformation. They grow. There'll be a number of them because there will be many grains who have almost exactly this orientation. And they grow and expand until they interconnect, percolate, and you begin to get homogeneous deformation of the whole material. Because of the complexity of this process, you're not going to get yielding when the most favorable grain equals tau c. There will be some other criterion necessary to get you to a general deformation of the material. That problem has been studied theoretically for many, many years. The result is that the yield strength of a polycrystal, if we measure by, say, the 0.2% offset method is shown here, is going to be some factor multiplying the critical resolved shear stress. This factor is called the Taylor factor after G.I. Taylor, who first proposed it, and it turns out to be about 3. So the yield strength for a polycrystal, random polycrystal, is about 3 times the critical resolved shear stress for dislocation motion on the favorably oriented planes. Well, what can we do to strengthen a material? And this is a very important thing in material science, because the yield strength of the material is the design criterion we have to use for many purposes. We want materials to behave in the elastic region, not the plastic region. The higher we can make the yield strength, the greater the strength range we have, the elastic range, which is the useful range for using the material in most applications. So we want to get the strength up as much as we can ordinarily, consistent with the need for the material to be resistant to fracture, for it to be tough. So what can we do? We strengthen the material by any mechanism we can use that inhibits dislocation glide. The simplest thing we could do is change the crystal structure, make the material so rigidly bonded that dislocations are very, very difficult to move. The critical resolved shear stress is very high. Alternatively, we can refine the grain size, or we can introduce things into the grains that act as obstacles to the motion of dislocations. Let's begin with the inherent strength. Well, I skipped the slide here. The inherent strength is called the Pyle stress, Pyle-Nabarro stress. And what the Pyle-Nabarro stress is, if we just imagine a perfect dislocation in a perfect crystal, we're going to have to put on a certain resolved shear stress to get that dislocation to move, because moving it is going to try the breaking and reconfiguration of bonds along the dislocation line. Well, you can make kind of a general calculation from the continuum elastic theory as to what that stress should be, and that lattice resistance, the Pyle stress, turns out to be given by a formula something like this, which has 2 major elements in it. G is the shear modulus. You know that tau is proportional to the shear modulus. The other crystal, newest Poisson's ratio, doesn't play as big a role. The other crystallographic factor is h over b here in the exponent. H is the distance between slip planes, b is the Burgers vector. Particularly because of this factor, when we get to materials that have very big Burgers vectors, because they have complicated crystal structures, and the Burgers vector has to be a repeat distance of the crystal structure. So if you have things with complicated crystal structures, the Burgers vector can get very big, and as a consequence, this factor becomes very small, and the Pyle stress gets very big. Materials like that are up at the high end of this curve. Here's a plot of the Pyle stress over the shear modulus as a function of h over b. Materials at the high end here are materials that are very, very difficult to deform by the motion of dislocations, because the dislocation can't move until we get very, very close to the ideal strength of the material, where the bonds themselves will tend to come apart. So these materials, like alumina, like silica, like silicon actually, are very difficult to deform by dislocation motion at room temperature. And they're up here at the far end of, of the Pyle stress. Materials at the middle of the Pyle stress, or the low end of the Pyle stress, excuse me, are typical metals and ionic crystals and such things. These are relatively easy to deform. And in fact, when the Pyle stress gets below about 10 minus 2 of G, in this whole region down here at the lower end of the graph, the Pyle stress really isn't all that relevant anymore. Other strengthening factors become dominant, and you don't really see the Pyle stress. The Pyle stress, the inherent resistance to deformation, is only important up here, where the geometric factor is very big. The advantage in these materials, as I said last time, and I will re-emphasize, these materials are very interesting because they can have true elastic behavior over a very wide range. So if you want, for example, to make a spring that will not undergo transient deformations when you use it, you use these materials. Any other thing where you want to be sure that your behavior is purely elastic, under significant stresses, you want to use these kinds of materials. The problem with these materials is while they are relatively very strong, they also tend to be very brittle for reasons we'll talk about a little later, and for that reason have very limited engineering applications. You don't make many structures out of glass for fairly obvious reasons. It breaks. Not that it isn't strong, it is strong, but it breaks. Therefore, you don't use it that much. You use materials down here, which can be both strong if you treat them right microstructurally, and also can be tough and resistant to fracture. No, this isn't working. Do this. The one simple way to control the strength of a structural metal is by refining its grain size. And you can do that using, in the processing of a metal, by using recrystallization. You heat it and beat it. You deform it heavily so that you induce recrystallization, heat it up so recrystallization happens, and then capture the grain size at a value that you would like it to have. There are other ways to get fine grain size, but that is the simplest and the one that you ordinarily do. In fact, you did that in a lab earlier this semester when you deformed copper and watched it recrystallize, and you saw the change in strength, the hardness that happened as a consequence of that. You can, in fact, in iron, get to very, very high strengths in this way. The problem with using grain refinement to get to strengths above, some intermediate value, about 1 micron is about the lowest practical grain size you'll use in steel is the following, that as you get to grain sizes down below about 1 micron, while the strength becomes very high, the elongation becomes very, very low. For all practical purposes, these behave in a brittle manner. They don't really fracture brittlely. They become plastically unstable, net down, and break that way. But the elongation is so little that you really do not have useful elongation in the material. And as I mentioned, in many structural applications, part of the specification on the structural material will be the yield ratio, which is essentially the ratio of the yield strength to the ultimate tensile strength. And they will require that to be below a certain number, which guarantees them a reasonable regime of plastic deformation. That's a safety factor. If you inadvertently exceed the yield strength, you want to have enough hardening in the material that the result of exceeding the yield strength will be minor deformation of the material rather than fracture. You know, as an aside, it's simply a fact that when you actually make a device, there are all sorts of nooks and crannies in any device that you make, that the minute you turn that device on, there will be places where the yield strength is exceeded. Notches, corners, various such things. There's even a phenomenon called shakedown in machine design, where you operate the machine and you expect to see some transient deformations. The behavior of the machine will change slightly after you turn it on. And what's happening is that these places where, just because of geometric constraints, you're developing high stresses, in those places you're getting deformations, the machine is just relaxing itself so that the parts fit. And that's a natural phenomenon. Well, if you have a stress strain curve that looks like this, no problem. You've got plenty of cushion for that little kind of deformation to happen. If your stress strain curve looks like that, the game is over, because the minute you get any deformation at all, the part's going to break. So you really do need this kind of cushion, and it's designed into materials. The alternative way of hardening a material is by putting obstacles into grains that inhibit dislocations. And there's kind of a universal model of obstacle hardening that we can use. It's pretty simple, and it kind of works like the following. Suppose we have some obstacles in the material, imagine them to be local points, that resist the flow of dislocations. And suppose we now put on a shear stress, remember that puts a load tau b on the dislocation, which will try to move it forward, so the dislocation moves against those obstacles. Well, where the dislocation impinges on an obstacle, it gets pinned. Where it gets pinned, it bows out like that. Where it bows out, there's going to be an angle between the branches of the dislocation here at the obstacle. And what you can show is that, well, the force on the dislocation is tau b. The mathematics is in the notes. I won't go through it here. The radius of curvature that the dislocation bows out between these obstacles, if we assume an isotropic that the dislocation is a line with a constant line tension, its energy per unit length, then it will bow out between the obstacles to a radius line tension divided by tau b. It turns out that the line tension of a dislocation, to a pretty good approximation, is just 1/2 GB squared. The shear modulus gets into it again. So the radius of bow out is about the shear modulus times the Burgers factor divided by 2 tau. There'll be a factor on here, but essentially here's your number. If we have this radius of bow out between the adjacent obstacles, then you can calculate what the angle at the obstacle will be. Now, the dislocation line tension, dislocation has a tension, and if you imagine this to be a string at constant tension, then the two branches of the dislocation, the two arms right at the obstacle, are pulling against the obstacle because the dislocation is trying to get shorter. It follows that the force on the obstacle is 2 line tension cosine psi over 2. The line is pulling in the direction shown by the arrow here with the force T. There are 2 branches to the dislocation, so I get 2T, and the angle, the cosine of the angle, just cosine psi over 2. If I let cosine psi over 2 be beta, which is our usual variable in mechanics to discuss this kind of problem, then the force can be written 2 times the line tension times beta, where beta is the cosine of half the angle here at the obstacle. This is the force which the dislocation pushes on the obstacles. Now, any kind of obstacle you can put on a dislocation will have a certain strength. If this force exceeds a certain value, if this angle shrinks below a certain value, critical value, then the dislocation can move through or around the obstacle and go on in the material. So let's let that obstacle beta be beta c. If beta reaches beta c, the dislocation cuts through the obstacle and moves on through. If you do that, and if you assume these obstacles are randomly distributed on the plane, then you can in fact calculate, Jacques Verdel did it back in the early 60s, we did it by computer simulation in the early 70s, you get that the critical resolve shear stress turns out to be given by a fairly simple formula, twice the line tension of the dislocation, divided by the mean spacing between the obstacles, that's just LS, the Burgers factor B, the critical angle beta C to the 3/2 power. If I use the approximation that the line tension is 1/2 GB squared, then this turns out to be the shear modulus, the Burgers factor B, the obstacle strength to the 3/2 power, the square root of n, where n is just the areal density, the number of obstacles per unit area on the plane. And this formula works very, very well for all kinds of obstacle hardening. A couple of extreme cases, if you get an awful lot of solutes in, you may get a different formula. But basically, this thing works. There are 3 kinds of obstacles that we use, all of which can be done with that formula. We use solute atoms. If the solute atoms are randomly distributed, now the catch about solute atom solution hardening is sometimes the solute atoms will gather on the dislocation line, or they will cluster, in which case this relation doesn't apply, some other one must. If the solute atoms are randomly distributed, then the number per unit area is just the concentration C of solute. The obstacle strength of solute atoms is very low. It's about 0.01. Beta C is a dimensionless number. The second kind of obstacle we put in are dislocations. This is work hardening. If we deform a material, the material gets harder. It gets harder because dislocations are multiplying and they get in each other's way. In that case, the number of dislocation obstacles per unit area in the